So today is the second talk in a series, basically, mini series of 2 talks. So for those of you who were here last week, you will remember Sameela. So she presented basically one half of her PhD research last week. And because what she did was basically too much to fit into just one talk, we will hear about the second half today. Yeah, very exciting research at the intersection of software engineering and optimization. Yeah, so I think for those of you who weren't here last week, this is pretty independent and so I mean, obviously you missed the nice talk last week. You can, I think, catch up if you're interested, because that one was recorded. But you should be able to follow this one without any problem. Yeah, I think with that, I'll hand over to Sameela.
Thank you, Guido. So yeah, as Guido introduced, I'm Sameela. It's not working. Okay, and as I explained to you in my last talk, the overall idea of my thesis is to bring down the barrier between the domain experts and constraint optimization technologies. So today I'm going to introduce you to domain-specific languages to address problem drift. Now, before I introduce you to problem drift or domain-specific languages, I'd like to set the background like I did for last week. And those who attended my talk last week, please bear with me. There are a few slides that's repeating. So as we all know, the constraint optimization problems require finding a combination of choices that satisfies a set of constraints and optimizes an objective. Simply, when you're creating a roster, or even when you're packing your grocery bags, you're solving an optimization problem. And a modern approach to solve these problems is by using problem-specific models along with generic solvers. And we call this process model plus solve process. And in this process, in the first phase of this process, a modeling expert would convert a problem of a domain expert to a mathematically precise description, which we call a model, using a high-level modeling language such as Minisync, Essence, or Python. And then in the second phase, the models are instantiated with data to create problem instances. And then the problem instances are automatically solved using pre-built solvers such as Gurobi, Cplex to produce solutions. Now, a model, we'll say a successful model developed at the end of the model development stage can be deployed in a working environment so that the domain experts can use these models to solve their problem. But then the story really ends here, because even when deployed, the requirements and the operational context of the environment that we have deployed our optimization models, optimization systems, would change over time. For example, think that we've developed a model and installed it, and it is in use in a hospital. And then later on, the hospital actually, and that's to create the rosters, and hospital later, we'll say 2 years later, prefers to pair the experienced staff with the junior staffs in the shifts. And if there's no way to for this to be reflected in the model, then of course the model can still produce rosters, but then the solutions produced by the model would no longer be as satisfactory as it could have been. Similarly, if the hospital introduces a new shift type, now if that cannot be reflected in the model, of course, our model is no longer usable because it will create rosters, but then it will not assign the nurses for the newly introduced shift. So in that case, this type of changes could make the models obsolete. So changing requirements actually can make even the deployed systems to degrade in performance, fail, or in the worst case, even produce incorrect solutions. Now, in my thesis, I refer to this type of phenomenon with the word problem drift. Now, problem drift is a common concept that's been talked about in areas like machine learning. But then it's not been widely discussed with regards to constraint optimization problems. So at the moment, adding the changes introduced by the problem drift to a model is actually largely dependent on modeling experts. This is because creating the models requires a specialized skill set. And then at the moment, and it is difficult to convince domain experts to learn this specialized skill set to just to add few changes to the model. And also, at the moment, the domain experts are only indirectly involved in the modeling process by giving us, informal feedback or providing us with data and documentation. And as a result, the models that are developed at the end of the model development phase are not, most of the time, not understood by our domain experts. So they, most of the time, see our models as black boxes. And together, these reasons make it difficult for the domain experts to add new changes to the model on their own. And this limited flexibility actually makes our models, most of the time, because they cannot add these changes, the domain experts would abandon using our models. Let me share a story that we experienced we experienced problem drift in a real world case study. And the case study I've chosen is the problem fund allocation problem of the United Nations High Commissioner for Refugees, UNHCR for short. Now, UNHCR provides crucial assistance to people who are forced to flee due to conflict and persecution. And annually, they release a global appeal requesting for funds. And last year alone, it has been 10 billion US dollars. So as a result, they receive a large amount of funds, which are the donations, that needs to be distributed among a number of humanitarian projects. But these funds also comes with strings attached to them. For example, there are rules like this fund should be used only for a certain geographical area, like a region, sub-region, or a country. Or this fund must be used for a particular situation that's a crisis, like Middle East situation or Venezuela situation. And then it could also be earmarked according to the target of support, which they refer to as pillar, like refugee program and stateless program. And often, because of these constraints, some funds are actually left unspent, so which we call the excess, and carried over to the next year. And the target of the UNHCR is to minimize this excess amount, so more funds are available now rather than being carried over to the next year. And our story begins in 2016 when a domain expert from UNHCR contacted Peter Stuckey and Maria Garcia de la Banda to find a bug in a minisync model that they developed to solve this problem. And eventually, Peter and Maria ended up developing the model for them. And before I continue with the rest of the story, I'd like to present, I'd like to show you how the model that, I'd like to briefly introduce the model that's been used to solve this 2016 problem. So as we all know, an optimization model has parameters, which are the input data, the variables, which are the major decisions that must be made to solve a problem, objective function, which measures the quality of the solution, and constraints that imposes restrictions on parameters and variables. So in 2016, both the data of funds and projects in one table called item. And for the funds, there was an income with a zero budget, and for the projects, there was a budget with a zero income. And every item had a unique ID, allocation level, which decided on which geographical area the fund should be distributed, and that was particularly important field for funds. And then region, sub-region, country, pillar, and situation. The main decision that was to be made to solve this problem is to find out how much money has been transferred from one item to the other item. And it was modeled as a two-dimensional array with item as the index. And the vertical sum actually presented the total amount allocated from each item. So for projects, the total amount allocated had to be zero. And then the horizontal sum resulted in the total amount that's been received by an item. And for the projects, the total amount received must be zero. And there was there was many constraints related to the model, and I'm not going to go through all of them. I'll just explain one of them. And they were expressed in the form where it stated when exactly not to transfer money. So this constraint here says for if the allocation level of the from item is equal to region, and the regions of the from item and the to item does not match, then the moment should be equal to zero. And the objective of the model was to minimize the excess after allocation. In 2016, compared to the greedy algorithm that they used to solve this problem, the minisync model could reduce the excess for the same data set from $500 million to $100 million. So we were really happy about this result, and we happily thought that this model has been continually used to support their decision making. But later on, like a few years later, actually, we found out that that has not been the case. So their requirements and the operational model has changed, and the domain experts did not know how to modify the model to meet these new requirements. And so our model was no longer usable. But importantly, rather than reaching the modeling experts to add these new modifications to the model, they modified their greedy algorithm because they had the in-house expertise to do so, and then moved on. So in 2022, that is when I was involved in the project, when we revisited this problem, we could understand these changes were not that complex. They were simple and could have been easily added to the model by modeling experts. So just to give a feel of the type of changes that could be introduced with problem drift, let me go through some of these changes. So when it comes to the parameters, the main parametric change was that from 2016 to 2022 was that now the details of funds and projects came into separate files. And then the operational model also changed, where in 2016, the smallest operational unit was country, which was responsible for distributing the funds to the project. But in 2022, they subdivided that smallest unit, that is country, into few cost centers. So now there was a new attribute associated with funds and projects that defined to which cost center the funds and projects belong to. And then they also introduced two new other attributes, domain and account type, which marked which prioritize some of the funds and projects over the others. And the main variable change, in the sense, I would say the main decision that was to be made did not change, where in 2016 it was to find out the moment from item to item. But because we had funds and projects in separate files, in 2022, it was to find out how much money has been transferred from fund to a project. when it comes to the constraints, the new constraints were, what we noticed is like the new constraints were associated with the new attributes that's been introduced. I mean, the ones that I explained in the parametric changes. For example, in 2016, there was a constraint for region, the one that I explained to you. So if the allocation level is region and the region of the two items do not match, then we can't move money. So similarly, because they introduced a cost center, there was another constraint in the 2022 model saying if the level is allocation level is cost centers and the cost centers of the fund and project do not match, then don't move money from fund to the project. So and all the constraints, the new constraints also take the form of these if then else statements. And when it comes to the objective, again, the overall objective remained the same, but because we had to prioritize the allocation of some projects over others and some funds over others, like, for example, we had to prioritize the allocation of the carryover funds before we start allocating the other funds. So that had to be achieved through the objective as well. So we had to, so that had to be achieved through the objective. And so we re-implemented the model in 2022, which was not difficult. But then, and also this model could, convince them to adopt, convince them to integrate optimization technologies in their new enterprise resource planning system. And the thing to notice here is that even though we easily modified the model, this process actually required significant time and effort. And even with the new implementation, adding further changes to the model was fully dependent on the modeling experts. And also, problem drift could happen again at any point of time. So this made us think about what could have been done differently to make it easy for the domain experts to add simple changes to the model. That's when we came across the domain-specific languages. Now, domain-specific languages are formal languages with limited expressiveness focused on a particular domain. And in this approach, we first specify a domain-specific language and then use the DSL, so that's the short term, DSL to specify the requirements, and then these requirements or changing requirements are automatically translated into executable code. Now, domain-specific languages are quite popular in imperative programming paradigms for their readability because they can be designed in such a way that they are well understood within the domain, and for their reusability because MDSLs can abstract the common substructures and reuse them. And it also allowed control flexibility where you can actually minimize the possibility of errors. And so we propose to use domain-specific languages that are specialized for modeling, which we called MDSLs, to improve the flexibility offered for the domain experts to add new changes to the model. Now, introducing MDSLs inevitably extend the model development phase into two stages. In the first stage, we have to develop MDSL, and in the second stage, we can capture the changing requirements as a requirement model using the MDSL, and the requirement model can be automatically compiled into a executable model using the MDSL. So then comes the question, what should we allow the domain experts to change in an optimization model using an MDSL? Now, I'd like to start the discussion with variables because that's the most difficult part to model. That's the most difficult part to express in a model as well. So if you recall, from 2016 to 2022, there was a simple change where the moment was actually now modeled as a two-dimensional array between funds and projects. And that simple change actually required us to change all the other constraints in the model. And that indicates even a simple change to your variables can actually introduce extensive changes to all parts of all other parts of the model. And on the other hand, the choice of decision variables can have a profound impact on the solving algorithm. And selecting efficient ones most often requires a good understanding of the modeling language and also the underlying solving technology, which the domain expert not be aware of. And so we propose to reserve the choice of decision variables to the modeling experts. That means don't allow changes to the variables using an MDSL. And with that decision, of course, now our optimization model is split into two parts, where we have a fixed part, which we do not allow the modeling experts to change using an MDSL, and flexible model part, which can be automatically which can be automatically created by compiling a requirements model using an MDSL. When it comes to parameters, the parametric changes are very common, so therefore we can easily use an MDSL to introduce new parametric changes to the model. Having said that, we have to remember that not all parameters are equally suitable for modification. For example, in 2022 model, you already know that we use funds and projects to model the variable. And if we allow the funds and the parameters funds and projects to be removed using an MDSL, that would cause inconsistencies throughout the model. So to avoid that, they are better be placed on the fixed part of the model. So same goes with the constraints. Constraint changes are very common. Again, we can allow the constraint changes easily through an MDSL, but then some constraints are best kept in the fixed part of the model. For example, in 2022 model, we had general knowledge constraints like the funds cannot allocate more money than what's available in the funds. And then the projects can't receive more than the requirement of those projects. And those type of constraints are not going to change over time, and they are general knowledge constraints. So this type of constraint can be kept in the fixed part of the model. And objective function changes, again, is very common and specifically in multi-objective optimization problems. And we can use MDSLs to allow limited changes to the objective components as well. For example, we can allow to change the weights. We can, add and remove components from the objective, and even we can let the domain expert formulate new objective functions with basic arithmetic operators. And so, considering all these recommendations, I developed a prototype MDSL for UNHCR to add and remove to change the constraints of the 2022 model. So it was a simple model. I used JavaScript and developed it from the scratch. So what the interface allowed you to do is to specify a constraint using a collection of drop-down list boxes, and then while you're constructing the natural language, not the natural language, but a textual representation of the constraint was displayed. And once that's been added to the rule base, the rule base can be converted to the minisync representation. What you see here in the screen is the grammar that's been used to implement the UNHCR MDSL. I don't want you to read it, but then the takeaway message is it's very simple and very short compared to the full minisync grammar. So the MDSLs actually, because they are very short, this can be easy to learn for the it is easy for the domain experts to learn these languages. And this is an expression, like this is the region-related constraint that I already showed you in the MDSL syntax. So it can be read as, for every fund and project, if the level of fund is equal to region and the region of fund is not equal to region of project, then the moment from fund to project is equal to 0. And note that compared to the minisync syntax, the MDSL is much more, MDSL syntax is much more readable, and we can design it the way we want it. For example, we can take off the parentheses and then replace the double equal signs with like is equal to, rather than using the mathematical notation, but it's a design choice. And when implementing the UNHCR MDSL, I choose to implement as a projectional editor rather than a fully functional editor. So let me explain what I meant by this. So in a fully functional editor, you can enter random text into the editor, and this text needs to be tokenized and then passed to check the syntax and the semantics, and then only this can be converted into the other representation. So like that can be converted to the target language, in our case to the modeling language. In contrast, what we do in projectional editing is we create an abstract syntax tree and develop a customized editor that allows the end user to make direct changes to the nodes of the abstract syntax tree. And once you have, you can have multiple projections for the same ASD as well. And this is what we exactly did for the UNHCR MDSL. So this pane here is actually a projection of the abstract syntax tree using HTML constructs, the drop-down list boxes, and then the same ASD was projected as a textual representation, and even the minisync representation was another projection of the same ASD. Okay, so now that we've had a look at the application-specific MDSL that can be used to address the problem drift or changes introduced by the problem drift, the same concept actually can be used to create the different models for slightly different applications in the same domain. Let me explain this with an example. So if you construct a MDSL for a broader domain like nurse rostering domain, this MDSL can be used to create models for different hospitals, like the Austin Hospital's rostering problem model and Alfred Hospital's rostering model. That means MDSL created for a broader domain can be used for rapid prototyping. Now, I've also developed a prototype MDSL for nurse rostering domain to test this out. But before I show you the MDSL, I'd like to give some background about the nurse rostering domain. So what we try to do in a nurse rostering problem is to find for each nurse, for each day, is a shift being assigned and what's the shift type that's being assigned. And but the problems actually change from hospital to hospital. For example, the number of days in a roster may change, the nurse types operating in the hospital may change, shift types operating in the hospital may change. And from different hospital to like one hospital to the other hospital, they may also use different terminology to refer to the same concept. For example, planning period, roster period, planning horizon, referring to the same thing. And if we can capture these domain-specific terminology in the MDSLs, that is going to give a customized feeling for our domain-specific language. And then when it comes to the constraint, you already saw in UNHCR model, we had only one type of constraints. All the constraints could be expressed in the form of if-then-else statements. But when it comes to the nurse rostering problem, there are many types of constraints associated with the domain. For example, there are personal contact related constraints. So these specify a maximum or a minimum number of working hours, night shifts, or day shifts for a particular time period. So these constraints were actually dependent on the shift type operating in the hospital. And then when it comes to organizational requirements, there can be constraints like the maximum, minimum number of certain type of nurses required for a certain type of shift. Again, the organizational requirements are dependent on the nurse types and the shift types operating in the hospital. Now, there are many more constraints in NRP domain. I'm not going to go into detail because this is enough for the rest of the talk. And yeah, so considering those requirements, I created a prototype MDSL to capture the nurse or build prototypes, rapid prototypes for the hospitals. So when I was implementing the MDSL, I also got to know that the optimization solution providers most of the time use questionnaires and or structured interviews to learn about their client's problem. So I designed this MDSL in the form of a form, and because our domain experts are going to be the nurses that may not have a technical background, I use structured natural language to build the expressions of the MDSLs. So let's see how a rapid prototype for the Austin Hospital could be created using the MDSL. So first, it allowed to capture the domain-specific terminology so that you can give a customized feeling for the end user. And then you can specify the number of days, shift types operating in the hospital, nurse types operating in the hospital. And it allowed to express the constraints using these already defined shift types and nurse types. And once the constraints are being defined in the requirements model, this can be automatically converted into the minisync model. So the appearance of the MDSL may look like a user interface, but in fact, it is not a user interface. It's actually, it's not a traditional user interface. It's a user interface that is there to use this domain-specific language. So when it comes to traditional user interfaces used for interactive optimizations, interactive optimization problems, they may allow you to change the values of the parameters. They may allow you to change on and off parameters and constraints and even objective components. But it's very it's very rare, or you can't find occasions where they allow you to introduce new parameters or introduce new constraints to the model. When it comes to the MDSLs, we can use MDSLs to introduce new parameters and new constraints to the model. So it's much more powerful than a traditional user interface. And one thing that I also want to mention is that these MDSLs are not text-based. I mean, it doesn't have to be text-based, especially if you're using projectional editors. The expressions could be textual, graphical, mathematical, or tabular. For example, in the UNHCR MDSL, the NRP MDSL, I use a table to capture the organizational requirements, where you can specify the shift the nurse and the maximum and the minimum requirement for each nurse type and shift type. All right, so that we've had a look at the two prototype modeling domain-specific languages. I would like to walk you through the MDSL development process. So this typically have 4 phases: the decision phase, analysis phase, design phase, and the implementation phase. So in the decision phase, this is actually the phase that you have to decide and weigh out the potential benefit against the cost of implementation, because implementing a language, a domain-specific language, is prohibitively expensive. Again, as I said earlier, if you are considering to implement a user interface along with your model, then of course designing an MDSL is a better choice, because it's not much work. I mean, like the time-wise and the work-wise, it's not much work than implementing a user interface, but MDSLs can allow much more flexibility than a traditional user interface. And the analysis phase actually focused on studying the domain. So this is the phase that you have to find the fixed part of the model and the flexible part of the model. And we recommend to use constraint entity relationship diagrams that I introduced to you last week in identifying the fixed part of to help identify the fixed part of the model and changeable part of the model. And also the constraint entity relationship diagrams can be used to group the similar constraint together. So this is a CERD for the UNHCR problem. And you can see that highlighted yellow are the constraints that are likely to change, and all of them has the same all of them can be expressed using if then else statements. So once you have grouped the constraints, the CERDs can be also used to find the common substructures that's needed to express these constraints, which will actually help you in the design phase, where you have to define the syntax of the expressions. So when you're defining the syntax, you can use context-free grammars to define those. It's not a must, but it definitely helps help the implementation process. And when it comes to implementation phase, main decision that you have to make is whether you want to implement your MDSL as a fully functional editor or a projectional editor. And projectional editors are advantageous because in this way, you don't have to implement the tokenizers and the parsers. And also projectional editing can allow you to use range of notations in your expressions. But having said that, even with a projectional editor, implementing a language is costly. But fortunately, we have tools like language workbenches that would help to accelerate this process. The language workbenches are actually bundles the toolset that needs to build a new language in one place. And the JetBrains MPS and whole platforms are 2 example language workbenches that also allow projectional editing. And I used JetBrains MPS to implement the nurse rostering MDSL, and I quite like the tool because one, it allows a range of notations, like in your expressions, you can use tables, you can even use graphical components, you can use checkboxes and buttons in your languages. And also JetBrains MPS has a good documentation and also active forums, which makes it easy to learn the tool. So in summary, we have to admit that the problem drift is inevitable in real-world applications. And if we are unable to allow the domain experts to add these changes introduced by the problem drift to the models, it's very likely that our models, even when they are deployed, will be abandoned by the domain experts. So for continued adoption, we have to find ways to offer flexibility for the domain experts to add these new changes to the model without having to learn a modeling language. And so we propose using modeling domain-specific languages to allow control changes to selected components of a model by first specifying a requirement model and then automatically compiling that to the model. And the MDSLs designed for broader domains can be used for prototyping. Broader domains can be used to create rapid prototypes. So once it's developed, the modeling experts and domain experts can actually work together in the early stages of the model development process to create a rapid prototype using these MDSLs. And so together, the CERDs that I introduced in my last talk and also the MDSLs I just introduced to you make the optimization models transparent, trustworthy, flexible, and thus adaptable in real-world settings. And also, this collaborative approach propose a change from the traditional approach of modeling for domain experts to modeling with them. All right, so thank you.
Thank you very much.